All right, guys, today we're learning about nuclear decay. So, this is nuclear chemistry, and we always get like really nervous when we hear, oh my God, we have to work with nuclear atoms. That sounds really hard. They pay nuclear engineers the big bucks, and they do. But nuclear chemistry, I promise you, is not that hard. We just have to remember three different types of decay: alpha, beta, and gamma. Okay? So by the end of today, our goal is to be able to describe alpha, beta, and gamma particles and their relative strengths. And then our essential question is just what even is radioactive decay? So, really quick review. When we first started learning about atomic structure, we learned three different types of notation: nuclear notation, isotopic notation, and periodic notation. What we're going to talk about today uses nuclear notation. So the X number is the element symbol, the A is the mass number, and the Z is the atomic number. And that was just a quick refresher for our own memory purposes. In terms of nuclear reactions, there are three different types. You have your radioactive, nuclear decay, you have fission, and you have fusion. Fission and fusion might be words that you're familiar with, that you've heard before. We'll talk more about those later, but they typically have the exact same definition no matter how they're used. So if you're already familiar with the words fission and fusion, you probably have a good idea of what is happening in these two processes here. So in radioactive decay, what you're seeing is a nucleus of an unstable atom losing energy by emitting radiation. So you have a radioactive atom, which is unstable, and it releases energy by emitting radiation. Okay? Because all radiation is just energy. So to break that down, radioactive nuclear decay. Radioactive is just the ability of an atom to spontaneously or randomly release particles or energy from its nucleus. Nuclear means it's related to the nucleus, which makes sense because radioactivity is an atom releasing particles from the nucleus. And then we know decay just means to break down. We would have learned that in environmental science and also maybe biology. So, to put it all together, what this means is that an atom has the ability to randomly break down its nucleus by releasing alpha, beta, or gamma particles. Okay? Sometimes atoms are a little bit unstable for various reasons. Either they have too many neutrons or not enough neutrons. To fix that problem, they spontaneously emit or release different particles to become another element like that. And that's radioactivity. I don't know if you guys can even hear that snap. I told you guys I can't snap, but there it is. So they spontaneously emit or release different particles to instantly become another element, which means they are radioactive. There are different types of decay, okay? Your first two types are particles that are emitted from radioactive nuclei, but this does not happen together. An alpha particle can be emitted or a beta particle can be emitted. And then the third type is a wave, and that's a gamma wave or a gamma ray. Okay? Your alpha particle is just a helium nucleus. It's literally just a helium nucleus. So alpha decay is the alpha particle, which is a helium nucleus, which is your 4 as the mass number and 2 as the atomic number. Sometimes written like 4-2 with the fish symbol, which is the Greek symbol for alpha. It moves at a very slow speed. Its symbol again is here. Its mass number is 4 atomic mass units, which is why that 4 is up here. Its charge is a positive 2. And it's very weak. You can block it using paper. And in fact, The way that we test whether or not printer paper is too thin or too thick is by bombarding it with alpha particles. If a ton of alpha particles pass through the paper, then that paper is not thick enough. If only a few pass through, then the paper is perfect for printing. Your alpha decay example looks like this. You have a uranium-238 nucleus here. It's very unstable. This is what we call the parent nucleus. In order to stabilize itself, it's going to get rid of an alpha particle. It's going to get rid of some mass. It's going to get rid of a few protons. And it becomes an entirely different element. Thorium, which is here, with a mass number of 234 as compared to uranium's 238, and an atomic number of 90 as compared to uranium's 92. Okay? Remember when we were learning about chemical reactions, we learned about the law of conservation of mass, which states that the atomic mass on the left side must equal the atomic mass on the right side because matter is neither created nor destroyed. The same must be said for mass. It's only rearranged. Okay? So if on the right-hand side of this equation, we have radon, which has a mass of 222 and an atomic number of 86, and helium, which has a mass of 4 and an atomic number of 2. On the flip side of that, we must have something that equals this. So what you'll do is add the 4 to 222, which will give you a mass of 226. And you're going to add the 2 to 86, which will give you an atomic number of 88. And that changes the element. Why? Because the proton count or the atomic number defines the element. So now instead of radon, you have radium. So what you would put on this side is 226, 88, and then the chemical symbol for radium, which is Ra. Radium releases an alpha particle to become radon. When uranium-234 undergoes alpha decay, 235, I apologize, it does the same thing, okay? Alpha decay simply says that you release a helium particle, which always looks like this. Always. When it releases the helium particle, it loses 4 from the mass number and 2 from the atomic number, becoming thorium. Oops, sorry. So what happens when thorium-230 undergoes alpha decay? Somebody tell me. I'll give you guys a second to work the math. Okay, right. So 230, thorium-230 with a 90 atomic mass or an atomic number of 90 would become radium-226 with an atomic number of 88 when thorium undergoes alpha decay. So again, let's practice this. When cobalt-59 loses an alpha particle, what atom will it turn into? And then the next practice, write out the alpha decay for nickel-63. I'll give you guys about a minute and a half to do that. And then we'll come back and we'll show each other our answers by holding up our notebooks to the camera. Okay, cool. Let me see your answers. Hold them up to the screen. Mm-hmm. Good job, guys. So this is a sample question of what you'll see on a final exam or your midterm. This is how these questions are phrased. Okay? So they're going to tell you what the nuclear equation represents. And you need to figure out what's the mass number of the element represented by X. So we know the mass number is at the top in nuclear notation. And so the mass number should be 218B because element X loses 2 protons and 2 neutrons when it undergoes alpha decay and becomes radon. All right. So now we're going to move on to beta particles. Beta particles are related to your electrons, not your protons or your neutrons. Okay, so the particle that's shed is the electron. It moves very quickly. It has a symbol of 0, -1, or 0, -1b. It has a 0 mass because electrons are very small. It has a charge of -1. And it is medium strength, which means that you can block it by using aluminum foil, like regular aluminum that you find in your house foil. So what happens in beta decay is that you have a happy-go-lucky situation, a family, they're doing great, and then an electron particle or a beta particle shoots off as a result of random decay. So when something undergoes beta decay, what you'll see is that the mass number stays the same because beta particles have a mass of nothing, but the atomic number goes up 1 because the atomic number is equal to the protons is equal to the electrons. Okay? Even though this is a -1, you're adding to your atomic number. So this goes from cobalt to nickel. The mass number stays the same. Your atomic number is what changes. So, quick question. What element is formed when iron undergoes beta decay? Remembering that the mass number doesn't change, but the atomic number does. I'll give you a second to check your periodic table. Perfect. Mass number stayed the same, but your cobalt is the element that's produced because you're just going to add a -1 to that 26 and come up with 27. You guys try this on your own sheet of paper, and then after a minute, you will hold it up to the camera so I can check your answers. Okay, great. We're also going to practice again. I'll give you another minute and a half to write out the beta decay for these 3 isotopes. Okay, cool. Everybody hold your sheets up to the camera so I can see how your work went. Good job, guys. Beta decay is not too difficult. Again, now we're going to practice with an actual test question. Let's look at this and tell me what is the other product of this reaction. Okay, great. So because we were just talking about beta decay, this might have been easy for you guys. You should have gotten D as your answer. Perfect. Which element or which particle, sorry, will complete this equation? You should have gotten D, the alpha particle. Perfect. Great job. So now we're going to move on to our last type of wave, the gamma particle or the gamma ray. It doesn't produce a particle. It's a gamma ray or a wave. Its symbol is 00 and this fancy little V, which is the Greek letter gamma. It has a massive zero. It has no charge, and it is very strong. You can block it with lead. Gamma rays are very high energy radiation. So gamma rays are not a particle like our electron and our alpha particle or a beta particle and our alpha particle. It is a burst of pure energy, and that's it. So when a gamma ray is emitted by an element, what happens to the atomic mass and the atomic mass number? Or the atomic number, I'm sorry, guys. Recalling that gamma ray's signature is 0, 0, 0 for the mass number and 0 for the atomic number. Right. You should have gotten A, which is that the atomic mass stays the same and the atomic number stays the same. So really quick review for our alpha particle, our beta particle, and our gamma particles. Alphas are symbolized by the Greek letter alpha, which looks like a small fish. The formula is the helium nuclear notation. It has a mass of 4, a charge of positive 2, and it is very slow. The beta particle is the Greek letter beta. Its formula is here or here, either 0, -1 e, which is the electron, or 0, -1 beta. Its mass is 0. It has a charge of -1, and it is represented by, its speed and particle are high speed electrons. Our gamma rays are represented by the Greek letter gamma, which looks like a twisty V. Its formula is 00, twisty V, gamma. Its mass is also 0. Its charge is 0. And it is high energy, pure radiation. Now, let's discuss, is radiation helpful or harmful? We use radiation in multiple different ways in medical practices, as well as to help us uncover archaeological finds and other types of very relevant information. However, in order to utilize radiation, we have to protect ourselves. So, have you ever gone somewhere and be asked to wear a thick, like heavy sort of protective apron? I know I have. What's a time where you can think of having to wear something like that? Exactly. You might have had to wear something like this at your dentist office. Or if you've ever had an x ray because you've broken a bone or something similar, they would have placed an apron over you in the space that you are being x rayed to keep you safe and protect you, your organs and things. So, alpha particles are the least harmful to humans. You can stop them with a thin sheet of paper. Your beta particles can be stopped by a wood or a thin sheet, by a piece of wood or a thin sheet of aluminum. And then gamma rays are the most harmful because you can only stop them with a thick piece of lead. So we should never be exposed to gamma radiation without some type of protection. As you can see here in this example, as the arrow goes down, strength decreases. Your alpha rays are stopped by you. Beta rays go right through you, and then into the aluminum, and then gamma waves just keep on going. So earlier we talked about nuclear decay, nuclear fission, and nuclear fusion. We've covered all three types of decay. Now we're going to talk about energy. There are two ways that nuclear energy can be released from an atom. The first is fission, which is when the nucleus of an atom is split into two smaller fragments with a neutron, and fusion, which is when two smaller atoms, usually hydrogen, are brought together to form a larger atom. This process is how the sun produces energy, which we receive as heat. So imagine that you're going to play a game of pool, not that game that you guys play on your phone all the time, but a real pool, okay? What happens to the balls when you hit the cue ball? This guy who looks real concerned at the front. Right, they're going to scatter. Okay, they're going to fly in different directions. This is what's happening in nuclear fission. The racked balls, aka the balls in the triangular portion, are the atom's nucleus, and the cue ball is the neutron bullet. That's what's going to shake everything up and scatter everything across the field. Fission is the splitting of a nucleus into smaller fragments. It occurs when the nuclei of certain isotopes are bombarded or blasted, like with this cue ball, with neutrons. This is most common with uranium. It releases massive amounts of energy. We used it to create nuclear energy, and we also use it in nuclear weapons, like the bombs that we dropped on Hiroshima and Nagasaki in Japan. So this is an example of nuclear fission. Okay? You have a low speed neutron. It's captured by an atom, and then boom. Now all of these neutrons are shattering. So an example of nuclear fission is the A bomb. Again, these are the bombs that we dropped on Hiroshima and Nagasaki. Very small, only 2,200 pounds, but an atomic bomb can deliver an explosion which is equal to the energy of 2,200,000,000,000 pounds of TNT. So the bombs that we dropped on Hiroshima and Nagasaki killed over 200,000 people, and these ended World War II very quickly because who wants to combat with nuclear force, right? However, the effects of an A bomb are both short-term and long-term and tend to be very devastating, okay? You have people who will die instantly because they were very close to the A bomb's location drop, and then you'll have people who suffer from the symptoms for their whole lifetime, perhaps for a few years before dying, or even just for a few months. The surrounding area might not recover quickly either. Landscapes could be forever altered. The A bomb was a devastating thing, and we probably should not have used it. Chernobyl, and I'm going to link a video in the description box of this video. Chernobyl was a nuclear plant explosion in the Ukraine, which occurred in April of 1986. It killed 30 people over the span of 3 months, and it forced the evacuation of 50,000 residents of the city. It is still very dangerous to enter Chernobyl today because of how bad the explosion was. Fallout can affect you in different ways. It depends on where you live, so how close you were, when and how you were exposed. The closer to the nuclear danger you are, the worse the exposure will be. And it can also affect your children if you happen to be pregnant, or even if you're not pregnant, but you would like to be it someday and you are close enough, right? So if you are somebody who would like to have a child, always wear protective coverings when you are around radiation, fusion, or fission of any kind. These are examples of how nuclear danger can affect you. Okay. Fission is energy, and this is what power plants use to produce heat in nuclear reactors. And it's just the combining of smaller nuclei into larger nuclei. Again, this occurs in the sun and the stars. The fusion of hydrogen into helium in the sun's core is what generates its energy, and we use this to produce electricity. That's what our power plants are for. There are pros and cons for fission for fusion. The pros are that it's clean energy. There's no greenhouse gas. You don't have to worry about coal emissions. You can create virtually limitless fuel. There's no chain reaction, which means that it's easier to control or stop than fission. Little to no nuclear waste, and it's very low cost. But the cons are that it takes a while to start the reaction, and it's a very complex process. You have to have very high temperatures, and it's difficult to contain once the reaction starts, and it's costly to build commercial power plants. Okay, I'm going to link two videos here that I'd like you guys to watch. We love Bill Nye here. He's amazing. So I want you guys to watch these two videos that go more into depth about nuclear chemistry. And then come back and watch this short video with me. All right, guys. So that is that for nuclear radiation. Tomorrow, we're going to begin discussing half-life. We'll probably recover this just as a quick reminder because it is a lot of information, even if it's not very complex. I will see you guys then.